see here. I guess I'll pray again. Heavenly Father, we thank you again for this day, and just ask you to bless our work, help us to understand what we need to for the review, and also pray for the internet to start working again, Lord. In your name I pray, Lord Jesus. Amen. Of course, maybe God's will for the internet not to work. I wouldn't question that. Now, here I have, okay, so points of order. Number one, mission 4, I'm not collecting. You guys keep it. I'm going to post a solution. Everyone gets full credit. I hope that's an acceptable solution because we don't have time to grade it before the test. So it's going to fall on you guys. That's one thing. Another thing, with this being a kind of not class meeting, I don't want to give a quiz officially in this class, obviously. So, as such, I'm just giving a take-home quiz. Now, this take-home quiz is lengthy. However, again, I'm going to collect, I guess I'll collect it on the test day. However, I would qualify that with, understand the context is, I'm not going to grade your work. You don't have to turn in all the solutions. I'm really just looking for, a piece of paper that says quiz 5 with your name on it, and I tried some of the problems. That's all I'm looking for, all right? So, in other words, I know this is kind of confusing. I'm giving you free points. So, once I decided that I wasn't collecting it, I decided I could put as many problems as I wanted on it since I wasn't grading it. So I did that. And, and so here we have a collection of a bunch, to use the technical term here, of different problems. And so I figure what we'll do here is just meander through here and talk about how to solve some of these. And, I think what I'll do is I'll write on the board as we look at the problem statements. And so you guys can just kind of look through there and see, is there a particular one that we should look at. Tell you what, let me start with the ones where I don't want to write anything down. I'm just going to use words, so we'll start there. Which one of these can we kind of talk about without doing any kind of writing necessarily? Obviously, I'm not going to write out the solution to all of these in class, right? I just want to kind of give you a quick indication how you do this. So like problem 3, what you'd want to do here is, this is an implication proof, right? So the assumption that you'd make at the start of your proof is A is a subset of B and B is a subset of C, right? That's how we'd start. All right, so that's where the proof begins. Assume A is a subset of B and B is a subset of C. This needs to be stated clearly and cleanly at the start. You do not need to explain what that means in terms of chasing elements. Some of you are doing this like every time you're, So it's enough to say literally assume A is a subset of B and B is a subset of C, period. Next sentence, let X be an element of A, all right? And then you go from there. Your goal then is to use the data to prove that necessarily X is a subset of C, right? So that's how that goes. How about this one, problem 7? Can you guys negate for me the sentence, all dogs go to heaven? We'd say what? There does not exist a dog which goes to heaven, right? Is that right? Negate the sentence today. All dogs do not go to heaven. There are some dogs that don't go to heaven. That would be correct. I don't think I can say all dogs don't go to heaven. That's not the negation. Because the all is part, we have to, when we negate the all, it becomes that there exists, right? So, let's see here, how about this? Negate the sentence, integer 6 is even, or the moon is made of cheese. So this is basically, this is my P, this is my Q. If I negate that, it becomes what?
Not P and not Q?
Not P. Yeah, there's options, aren't there? Goodness, I'm getting rusty on these things. It's been like 3 minutes since I taught it. But yes, it's a good, what did you just say?
Not P and not Q.
Not P and not Q? That you're saying that's logically equivalent to not P or P implies Q? Is that what you're saying?
No, not implies. I was thinking or.
Where was I?
Oh, I guess I was doing 8 instead of 9. Sorry.
Oh. Yeah, my bad. I may have just skipped between them, incidentally. Oh, you're right. They're very similar, but they're not the same, are they? Because this one's got an or in it, and this one's got a then, if then, right? So, all right, let's see here. Let's start with problem 8. Negate the sentence, integer 6 is even, or the moon is made of green cheese. Okay, so very good. So that is, we're negating, oh, I see why you said what you said. So we're negating P or Q, right? And so to negate P or Q, we do what? Not P and not Q, right? By De Morgan's law. And let's see here. So that would be what? We would be talking about the integer 6 is not even, and the moon is not made of green cheese. That would be the negation for problem 8, right? Now, I realized that this question, I was trying to put this into one page, but I threw this together rather quickly, so don't read too much into typos and stuff here, right? But is this true? So this begs a question. Am I referring to the sentence or its negation, right? Because those are not going to have the same truth values, right? If one's true, the other's false, and vice versa. So I was actually thinking about the original sentence, not its negation, for the sake of this question. So, right. So if we think about the sentence, the integer 6 is even, or the moon is made of cheese, that is a true sentence because 6 is even, right? And all it takes is for one of the disjuncts to be true, then the disjunction is true. All right. Now, next, problem 9, our pattern is what? We're trying to negate an implication. So how's that go? The integer 6 is even, then the moon. So the negation is what? It's logically equivalent to what? Let's look back at my notes for a second, see if we can find. Internet's still not working. I would like to show you guys the solution to quiz 4, but mission 4 really, but I just can't because the internet's not working. Fun stuff. All right, so where was somewhere in here I've got, it was at the start, wasn't it? Let's see here. I guess we could figure it out if I've forgotten, but following our tautologies, here's a list of tautologies, right? Like, here's one. Of course, contraposition, we could use that. Well, that wouldn't negate it, though, would it?
Wouldn't it be
P and not, where, is that in here somewhere?
I don't know if it was
Okay, so
no, it wasn't it might have been a different.
we're looking for the negation of the implication. I don't, so you say it's P and not Q? Let's check. So this is, hey, this is something we should do today anyway, so it's good. We can check if she's right by doing what? Truth table. So we do P we do Q, right? I do false, 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 true, true, false, true, true. Here we've got P implies Q. Here we've got the negation of P implies Q. And then over here we'll do, what else do I need for yours? I need my not Q. And finally, P and not Q. So hopefully we'll see that the truth values of the negation of the implication and P and not Q are identical. So by definition, P implies Q is true in every case except for what?
True implies false.
True implies false. So just that third case is false. So the negation is mostly false, right? False, false, true, false. Not Q is true, false, true, false, right? And what's the last one there? So now we're doing P and not Q, right? So if either one of these is false, the result is false, right? Because it's and. They both need to both, in other words, they need to both be true for this to be true. So we've got false, false, true, false. So thus comparing, right? So if we compare this column and that column, we see what? The negation of P implies Q is indeed, as you told me, like 5 minutes ago, P and not Q, right? Very good. So if we put that into practice for the quiz 5 problem that we were looking at, where was that? I'll find it eventually. So in quiz 5, we were looking at if the integer 6 is even, then, problem 9. If the integer 6 is even, then the moon is made of cheese. So we do, so P is the integer 6, right? So we'd say the integer 6 is even and the moon is not made of green cheese would be the negation, right, of that sentence. Which some of you probably could have figured out just through just logic alone, right? Like your just intuitive, God-given logic. But we can also do it symbolically according to the scheme I just put up there, right? My question then is the given sentence in problem 9 true? No, it's not true, right? Because the antecedent is true, but the consequent is false. You're like, well, the moon is made of green cheese. I just redefined cheese to be moon rock. So I'd say, good. You have a future as a math major. That's exactly the right way to argue. Change the definitions to make your claim inescapable. All right, so let's see here. Let's see, do anything I want to talk about in words. Yeah. I guess there's nothing else I just want to talk about here. So let me just kind of open up the floor here. What would you guys like to spend the rest of the class doing? We can look at the solutions to mission 1, 2, and 3. I have those. If the internet starts working, I can show you the solution to mission 4. I will post the solution to mission 4 in Canvas as soon as I can. I have it. It's in my email. Yeah. And I should have the solution to quiz 4 posted as well. Later, same kind of issue. Quiz 5, I'm not going to post a solution to this. All right. So whatever you want me to solve, we got to talk about it now. All right. So the floor is yours, guys. Which one do you want me to try? No, to negate a biconditional, there's various options, but if I put like P if and only if Q, right? Then this is true, false, false, true, right? So the negation of the biconditional is what? False, true, true, false. Yeah? So to negate a biconditional, we can use this like logical pattern, if you like. The negation of a biconditional is true if what? Like basically, oh goodness gracious. So negation of, I mean, put it in words, the biconditional is false if what? If what? There exists. Oh goodness, I'm sorry. I'm getting sucked into the question of like quantified versus propositional things here. I mean, it's going to be false if there's a case in the context of the discussion where P and Q don't have the same truth values, right? You're asking me about a specific problem, though, right? Like, which number 5? Then negate. Okay, yeah, we can do that. Negate. Let's be more specific. I'm kind of getting up in the clouds here. Negate the sentence n cubed is odd. Let's just do that one, right? So n cubed is odd. If and only if what? Seven n plus 2 is even, right? So what would the negation of this look like? There exists I think you're right. You asked me about implications at the start of this. So there's 2 ways you could go, right? I see what you're saying. I think I see what you're saying now. You're like, so really we've got P if and only if Q. So I see your strategy. That's a good strategy. I like it. So P if and only if Q is logically equivalent to what? P implies Q and Q implies P, right? So if I'm going to negate what I just wrote, that's a pretty simple matter because we have tools to do that. At least tools I remember. All right. So, like the negation of P if and only if Q is obtained from the negation of this biconditional, right? Which is, but we can do what? So this is the negation. So we De Morgan's law, right? So we have the negation of P implies Q, or the negation of Q implies P, right? And by our previous discussion, what's the negation of P implies Q? Well, P and not Q. Or
Q and not P.
Q and not P, right? So putting that into words here to negate the sentence. So I'm thinking of n cubed is odd as my P, and 7n plus 2 is even as the Q, so to speak. So to negate that sentence, that biconditional, we can simply say, okay, so P is, n cubed is odd, and 7n plus 2 is not even, right? Or 7n plus 2 is even, and n cubed is not odd. Of course, you could take not odd and not even and restate them as even and odd, respectively, right? So like, I'll put it up here. So we have n, well, I don't know. Let me not write everything out, actually. Is that clear what I said? Yeah. Huh? Go ahead.
Could you also negate it just by negating one of, like, either P or Q, and just writing not P and only of Q?
Not, so you're saying it's the same as not P if and only if Q? Well, I'm not sure, but the truth table will be the judge. So if you'll allow me this short manga style addition, not P I'll put over here. True, true, false, false. All right, so not P or if and only if Q. That's true if they have matching truth values, right? So not P, Q, false, false.
Oh, you put it to the wrong one.
Oh, I put in the wrong one. Rats. What were we doing?
Not P and Q.
So we're trying to judge not P if and only if Q versus what? The negation of P implies Q, is that right? All right, so I'm supposed to look. So these are, I'm looking at these ones. Okay, so I got false. Oh, that's true. Thank you. True, because false and false matches. Not P if and only if, so that's false, right? So then I need to compare this to what? This thing. And yeah, cool. Excellent. So another way we can negate a biconditional is just to negate one side of it, right? And I already know what's going to happen. It would also be the same as P if and only if not Q. That's another way to negate the biconditional. So, if you think about two propositional inputs, there are 16 different possible logical operations, right? I'm most familiar with and, or, implications, biconditional, but, there's a lot of different ways to repackage these and negate them and so forth, so. Let's move on here. I'd like to get away from propositional calculus and talk about the other stuff. So anything particular you guys want to look at in here? I'll get the ball rolling. Let's do problem 13. That one's easy. And we didn't do anything quite like it. I don't know if we did or not. I mean, it's been a while. So suppose A and B are real numbers and AB is equal to 0. That's how I'm going to start. I have AB are real numbers, and I'm assuming AB is equal to 0. All right? So if A is equal to 0, then A or B is 0. So we're done. If A is not equal to 0, then AB equals to 0 implies AB divided by A is equal to 0 over A. It's making me nervous to erase this, but I'm going to. Which then tells us what? The A's since A is not equal to 0, right? I couldn't do that in my previous case because A was 0. I can't divide by 0, right? But if A is not equal to 0, I can divide by it. Hence what? B is equal to 0. Therefore, in all cases, A is equal to 0 or B is equal to 0. So here is a nice, simple, direct proof that involves case-wise logic and just basic properties of real numbers, right? This same problem could be given if I just said, A and B were like rational numbers. It wouldn't change a thing, would it, In fact, you could still make this proof using integers, but then the division step, you kind of have to leave the world of integers, which I think is okay because you know how to divide integers. Other people would say, no, you can't do that because it's the integer proof and you can't use non-integer math in the integer proof. And I just don't really ascribe to that. So, okay, so I have no way of making you forget. Let me shut up. At some point, this is going to become hypocritical when I don't allow you to do something that you know how to do because I want you to do a different proof. So anyway, let's go on. How about if A, B is odd, then A and B are odd for A, B, and Z. Can we do that one? Let's do that one. So if A, B is odd, then A and B are odd for A, B, and Z. This was problem 16. That was an if. So what I'm going to do for this one, I'm going to say by contrapositive, right? This one just screams use contraposition to me. So suppose A and B are even integers, right? Then A is equal to 2J and B is equal to 2K for some J and K and Z by definition of even, right? Then what? Did I give you guys, everybody here have the sheet? Some of you guys came in once the university opened. So, let's see here. Did you already get one? You got one. Everybody else got one? And I also have let's see here. So, you guys, what's the next step over there? What do we want to do? We want to look at what AB AB. Yeah, I should have the solution to this later, guys. The internet's not working at the moment, so. But anyway, also I forgot to scan the solution, which is equally problematic for the quiz. But I have the solution. I just, Okay, so we look at AB then, right? Consider AB is equal to 2J times 2K, which by the way is 2 times 2JK, where 2JK is an element of the integers, thus AB is even. Hence, AB is not odd. Thus, using contraposition, we find AB odd implies A and B are odd. So that's that one. Yeah.
Not that I think it would change much for everything, but would we also have to look at the case where like A is even to B is odd, or vice versa, as a negation of A and B are odd? Or basically use the same logic, but.
Yeah, hold on a second. You might have a point there. AB is odd, then yeah, that comma is dangerous. I think I may be deceiving us. You're not making a, you're actually making a somewhat significant correction here, right? So A and B are odd, right? So when we negate that, what should I have? What should I have here? What's the negation of A and B are odd? It's what? A not odd or B not odd, right? So I shouldn't, the negation's not just A and B are even integers. What is it? I need to do what? I should say, suppose, yeah, I should say A, suppose A is even or B is even, right? So I'm sorry, guys. This has not been a good week for me. Then, without loss of generality, suppose A is equal to 2J for some. Oh, I'll just start over. Son of a gun. All right. It's essentially the same proof, but it's enough different that if I try to correct this one, it's not going to be helpful for you guys. So let's start afresh. It's still by contrapositive, but I need to actually negate the consequent properly and not just in such a way that I'm setting you up for the fail on the test next Tuesday, right? Because I definitely don't want you to negate A and B as not A and not B. That's not the negation of A and B. So, you know. All right. So I must negate the consequent, and that means that A is even, suppose A is even or B is even. All right. Without loss of generality, assume A is equal to 2k for some k in the integers. The reason that's a reasonable thing to say is the way that A and B appear in this claim is symmetric, right? There's no distinction in their roles, so logically speaking, it doesn't matter if I assume A is the even one or B is the even one, all right? And of course, if they're both even, I just erase the proof that that works, but anyway, then AB is equal to 2KB, right? Which, by the way, where K times B is a what? Isn't it? It's an integer. Thus, AB is even, that is, AB is not odd. Thus, by contraposition, A, B odd implies A odd and B odd. Thank you. That was a very, very helpful question. I do appreciate it. Guys gotta keep me honest in here, you know. If others of you knew this and didn't say anything, it's not nice. So which one do you guys want to do next? Yeah,
I have a specific question about 24.
24. Yeah.
So in order to prove that those are not equivalent, is it enough to just like find one instance where they're not equivalent, or do you have to prove that it's not equivalent for all instances?
Ah, good question. Let's write it up here. So let's see here. If x and y are elements of 0 to infinity, right? Then the square root of x plus y is not equal to the square root of x plus the square root of y, right? Now, I think that in the current language, this is a for all claim. So no, I can't just give a particular instance of its failure. That wouldn't be enough, right? I mean, I need it's not equal for all positive integers. Now, of course, if the claim was there exists x and y such that x squared of x plus y is not equal to the square root of x plus the square root of y, then sure, yeah, one example would be sufficient, right? Give me a second here. So how would we prove that then? Is probably your next question, right? So the answer for me at the moment is I'm going to cheat a bit and look where I got this. Let's see here. So it's somewhere around page 31 of something I have. Let's see if we can recreate the magic in here. You don't need to go over to that, Daniel. I mean, I guess you can if you want. Did you? I guess I should probably blow it up if we're going to look at that. So here is the proof. So suppose that we have x. So R plus is notation for 0 to infinity, okay? Suppose we have x and y and assume that they're equal, right? Towards a contradiction. If that's the case, if we square both sides, we get that, right? So I'll write over here. Towards contradiction, suppose square root of x plus y is equal to the square root of x plus the square root of y, right? That's the negation of this equality. Then squaring the equation yields x plus y is equal to the square root of x plus the square root of y squared, right? What is that? Which is equal to, of course, x plus 2 square root of x square root of y plus y. Goodness gracious, what on earth is going on with my phone? Which then, of course, algebra shows us what? This is what? We have x plus y is equal to x plus 2 times the square root of xy plus y. I mean, actually, I'm not sure that this step is even needed, guys, right? But what does this imply?
Times the square root of xy is equal to 0.
Right, 0 is equal to twice the square root of x. Or if you like, we could just say, it implies that the square root of x, square root of y, I'm going to go back to this actually. It implies the square root of x times the square root of y is 0, right? We don't need this. I may not bring that into the game. We don't need that even. Yeah? So we have this. But by the thing we proved earlier today, what's that say, since these are real numbers? square root of x equals to 0, or square root of y is equal to 0. Which then implies that x is equal to 0, or y is equal to 0. And this is contradiction. I have never had so many texts in such a short time as right now. What is going on with this phone? I don't even know. So that's a contradiction, therefore what? Why is it a contradiction? Since x and y are both what? Positive, right? Therefore, the square root of x plus y is not equal to the square root of x plus the square root of y. But yeah, a great question. This one, given the wording, it's definitely a for all statement, right? So, so if you're wondering, by the way, let me I'll tell you the man behind the curtain, so to speak. I got notes from a very good student in one of Dr. Sprano's Math 200s last year, and I've taken those notes and I've collected from them all the most interesting examples that he presented in the first month of class or something. Those are what's on your quiz 5. So I figured that should help round out whatever I've missed. It should all be there. If I get permission from that student to post these for you guys in Canvas, I'll do that, because the solution to many of these is in there. They are notes written by a student in class, so there's going to be some errors here and there. So with that understanding, supposing that they let me post it. I mean, I put it on the YouTube, but probably should ask before I post it in Canvas. That just makes sense. I'll shut up. What is this in problem 18? If A was, well, how do you read that? A line with a squiggle through it. It's line with a slash. What does that mean? Yeah, that's right. That means if A does not divide BC, then A does not divide B, and A does not divide C, right? So the way I would prove that would be to suppose A does not divide BC, and then I would assume that A does divide B, or A does divide C, right? And then I'll be able to argue that that implies that A divides BC, which is a contradiction. Consequently, it has to not divide it. So I'm probably going to use a contradiction to prove problem 18. But it is an implication, so I'd start with the assumption that A does not divide BC. For problems 19 and 20, those are case-wise. Those are case-wise logic problems. Since I've got this thing out, I guess I'll go back. I think those are on page 17 of this thing. Well, here's the, let's see, this one, the one I just got to on page 17. I think that is our problem 12. I'm going to be lazy and use this for a minute. I'm not sure I can use this, though. I'm not sure it shows up for the camera, unfortunately. Goodness. So this is positive rational numbers. Prove if n squared plus 1 over n is less than or equal to 1, then n cubed is less than 2n plus 3. So here's the argument which is given here. Suppose that that's true. Multiply both sides by n, which I can do because n is positive. It doesn't spoil the inequality. Then that gives me n squared minus n plus 1 less than or equal to 0. And then subtracting n from both sides gives me this. But then that gives me n minus 1 squared is less than or equal to minus n. All right. Which says what? It says there's no such n, right? Because that's impossible. We can't have a square of an integer to be negative. So what does that mean? That means that the implication, the antecedent, is never true. right? So you can write whatever you want over there. It's true. I can replace this with any inequality that you you do so choose. I could put anything over here, and the same argument works. It's kind of nasty, isn't it? But there it is. Let's see here if I have another one. Let me look ahead a bit, if I can find it. Here's this right here. Actually, was a proof of the homework. So, like in the homework problem that we had, show that there exists a pair of irrational numbers that one irrational number raised to the other irrational power is nevertheless a rational number. And so, like, I kind of give you a hint to use. Yeah.
Can we just assume E is irrational and natural log of 2?
We didn't prove natural log of 2 is irrational. So, no. Because I said in the problem I don't have up, I said using things we proved in class. So you were right. In as much as the video I made Tuesday counts as class, we have proved E is irrational. But we have not proved that the natural log of 2 is rational. I gave an indication to how you could prove it, but we didn't actually do that. So an observation that the digits in the natural log of 2 are not repeating is evidence towards it not being irrational. If I had a proof that it doesn't have a repeating decimal expansion, that would suffice to prove that natural log of 2 is irrational, but I haven't given that. But we don't need that, see, because there's something else we could have done, which is to look at the square root of 2 to the square root of 2 power. All right, suppose that that's irrational. Well then, if you look at the square root of 2 to the square root of 2, what's going on here? This is tricky. Well, yeah, I mean, that's law of exponents, right? If I have the square root of 2 to the square root of 2 to the square root of 2, that's the square root of 2 squared, which is 2. And of course, the square root of 2 squared is 2, which is, I mean, 2 is a rational number. That is true. I'm not sure I entirely understand it, but there it is. But I did see something like this in a book when I made up that problem. So, all right, anyway, let me stop talking about this. Do you guys have any questions about the test? Yep.
Is number 20 true?
Oh yeah, that's supposed to have less than or equal to. Otherwise, no, it is not true. It's definitely not true. So in fact, the only way that can be true is what? Like as I forewarned at the start of all this, I made this morning because I found out we weren't going to have official class. So I just wanted to give us a little bit something bigger to bounce off of. So I made this in a hurry. But yeah, that's supposed to be less than or equal to. This is the triangle inequality. So I think you pretty much want to break into cases to solve that, right? Think about it this way. Either x plus y is positive or x plus y is negative. And at least that was the proof that I found looking at things this morning. But let's go back and look at my solution to the homework problems before we run out of time here. Let's see here. So mission 2, we started with some symbolic logic. I haven't really hit on that at all in this quiz 5. I wouldn't, don't read too much into quiz 5 in terms of it being representative of the test. It's not. So for one thing, let's see here. So I started out with just, these writing symbolic statements into sentences. I don't really have much to say about those here today. And then we talked about how to negate a quantified statement step by step like this. So those problems are, I think, pretty clear. It's likely I give at least something like that on the test. I mean, I do expect you to know how to negate quantifiers. I would expect there's at least some proof, some truth table stuff on the test, but not too much, probably. Let's see here. This one, problem 15, the statement below is false. For all ABC, there does not exist a unique why not, such that the graph has a minimum. And then I let you modify the statement. Now that opens up Pandora's box for me, because modify the statement has a lot of flexibility in it, doesn't it? But I was looking for something like this. If you assume that A is the leading coefficient is positive, then it's parabola which opens up. And then it has a unique minimum at y equals to y naught. And so the proof of that is pretty much completing, well, there's different ways to do it, I suppose, but I think here I use calculus, so I differentiated it. Found that the critical number was at minus b over 2a. Noticed that the second derivative is positive, therefore by the second derivative test, it's a minimum. And what is that minimum? It's y naught, which is f of minus b over 2a. And of course that gives you the value of the parabola at the vertex. This could have been done algebraically. You don't need calculus for this one. We can just complete the square, right? Factor a out, take half of this, square it, subtract that piece, and rearrange. You can see that this quantity is smallest when this is 0, and as such, that's the minimum value. It's just manifestly evident from that formula. Surely there are questions on the test about even and odd numbers and proofs involving that, right? So it's important that you work with the definition. Telling me fuzzy sentences about how even and odd numbers go together, giving me examples, will result in like 0 partial credit. You must work with the definition. You must give proofs that are similar in content and spirit to like what we've done in the solutions here. And a lot of you are doing that, but there's a few who are not, yeah.
Will there be topology questions on the test?
There could be a topology question on the test, but it'd probably be packaged with, if I put that on the test, I feel like I owe you the definition of topology again. I don't expect you to memorize the definition of topology, but I might expect you to work with the definition of topology like you have already. In particular, like what's the definition of open, what's the definition of closed. Yeah. There does not, so I'm kind of running out of time here, but I'd like for you guys to have studied the solutions to the missions that I've given you. And I do tend to try to ask questions which are seeing whether or not you've actually done that, So like this problem, for example, is something that I had to think kind of hard about, but we really haven't talked about it much. This proof that every integer is either even or odd. It's kind of troublesome at the moment to do that, because essentially I had to look at division, So if you look at this argument here, that's what it took. Now, if I have a number which is both even and odd, I end up with the equation twice an integer is equal to 1, which ends up telling me that 2 is equal to a fraction, right? Which is absurd, because of course 1 over m minus n is not an integer unless m minus n is equal to 1, in which case 1 over m minus n is equal to 1, which is not equal to 2. On the other hand, if m is equal to n, then I have this, which implies 0 equals to 1. So any way you slice it, if we have an integer which is both even and odd, we can derive a contradiction by the arguments I just showed you. I haven't dwelt on that, but that logic that every integer is either even or odd lays in the background of a bunch of different things we've done, you know. There's some proofs that we just have to do a case-wise analysis, you know, where like in order to prove the thing you have to say, well, it's an integer, it's either even or odd. Then you give a proof in the even case, you give a proof in the odd case, and you put them together. I think that was that divides by 8 problem is the one that comes to mind. Anyway, let's see here. You know, proving the square root of 2 or the square root of 3 is not a rational number is something you should be ready to do. All right? And you need to kind of come to terms with what's the best way for you to say the argument. I've said it a couple different ways, but it has to involve the prime power factorization, right? That's really, I think, the critical thing in all this. I think the proof I have in the solution here is better than what I gave in class. So I think the one I gave for the square root of 2 is not as nice as the proof I gave here for like square root of 3. The other thing I would say is some of you need to do some work on like inequalities. So you're kind of floundering, so to speak, on the inequality problem on the quiz. Not everybody, but some, and so that's something you need to fix because I will likely ask about. There's going to be questions about inequality, like it's going to happen. And it might be one of these sort of cut and dried, you can use a sign chart to solve it and find intervals. But it doesn't have to be that, right? There are other ones that require step-by-step logic. We've worked some of those in here, not a lot, but thinking of... There's one I spent like 20 minutes on in class over on that board. I don't remember which day it was, but it had like an X and a Y in it, I think. Let's see here. This one was dumb. So I'm sorry. I wanted to make this more interesting. But obviously, I made that X squared where I should have put an X, right? If I put an X there, it would have tested you better, but it is what it is. Prove the sum of 3 consecutive integers is divisible by 3. So, I left this in my solution because I wanted you to see that I do stuff like this too. I mean, a lot. I'm like, I need to prove the sum of 3 consecutive integers is divisible by 3. I'll look at x times x plus 1 times x plus 2. That makes sense. Writing. I can't get it. What's going on? Oh, sum, not product. Words matter. So, a sum, when you add 3 things together, and if you do that, it's manifestly clear that you get 3 times an integer, right? You don't even need to break into even odd cases for this one. It just pops out at you. Yeah.
When it comes to proofs that are about like equivalence of sets, is that pretty much always going to have to use double containment for the proof, or is there any case where you wouldn't have to do that?
There are cases where you don't have to do that. In fact, in Mission 4 solution, if we could look at it, you would see that I had written some biconditional proofs, and in like the last, the videotape lecture, I gave a column style biconditional proof of the equivalent, the fact that 2 sets are equal, by showing that they have the same elements, and that's usually achieved by like a series of if and only if statements, which are a little more than just basically applying the definitions of intersection, union, set difference, Cartesian product, as well as paired with the basic tautologies, like the distributivity between and or, and how negation works, things like that. So it's not written in stone. It has to be by like a double containment proof, but oftentimes that's helpful. What is written in stone is like you can't just use set properties to prove properties about sets in here. Almost without exception. If I ask you to prove something about sets, you need to be working with elements and chasing where the element goes, how it works, the definition of the union, the intersection, those kinds of things applied to specific elements to prove the assertion which needs to be approved. You can't just give me fuzzy sentences and tell me